Welcome everyone to the Astronomical Society of Edinburgh. If there are any visitors here, welcome. I don't know if there are, but you're welcome and chat to us afterwards over tea and coffee. This is our main meeting of the month, and it's also our AGM at the end. So for YouTube viewers, we will turn it off before the AGM. You don't really need to see that, it's not very interesting, but for our society, it's an important bit of business. And we will be electing a new council, so this is my last as president after 4 years. This is what we've got coming up. We've got just a couple of slides on one or two things, and then the main event of the evening is Dr Geoff Vasil. He's talking about, I don't know if I've got the title of your talk right there or not, but you can update us if it's not quite right, about how the sun had its spots. Sean, our secretary, finally back. It's great to see him again. Will be telling us about the sky in the summer, since June is a difficult month to talk about by itself, and as we're going to have a break over the next couple of months, that's a good time to do that. And then we'll turn YouTube off and we'll have our AGM, just a small amount of business there, and at the end we have some tea and coffee, so hang around for a chat, please. If you're on Zoom, time to mute your microphone. This is something that I've mentioned in the newsletter, but it is open to everyone, whether you're a BA member or not. So the BAA Comet and Meteor sections are having a joint meeting in Edinburgh in October, and we are hosting it on their behalf here at the AUC. That's on the 4th of October, it's a full day. Lots of interesting talks and speakers, that's the programme there, lots of interesting people to listen to, including our own Douglas Heggie, who's talking about our own comet work here as well. It is just a nominal charge, just to make sure people actually bother to turn up and don't just get tickets for free and not arrive. We have most of a dozen helpers now, so all lined up to help us. Thank you very much for that. And you are welcome to attend. Anyone can do that within the society or outside it, or whether you're BA or not. And if you go to our website, you'll find an event on the front page there with all the details in there. So we're almost at our summer break in July and August. On Wednesday next week, we have our monthly imaging and observing group for our members, and that's online on Zoom. And then on the 20th of June, the last of the session is an online-only one on Zoom and YouTube, and that's by Dr. Isabel Book about supernovae and the search for dark energy. And then July and August, we are off. There'll still be the occasional newsletter coming out, but basically we have some downtime. And then we'll be back on the 5th of September here again. Professor Brad Gibson, who's spoken to us online before, but will be here in person telling us about liquid mirror telescopes. And it's over to Geoff, so thank you very much, Geoff.
Okay, fantastic. So again, I was saying thank you very much for inviting me. This is a pleasure. And so I don't quite know what to say. I mean, I'm going to say stuff that I think is very fun, but I don't know what the audience here knows. So, and I'm not saying this to apologize. I'm saying this because the sun is a very unique astronomical object. I think it's kind of obvious. It's the oldest, I think, astronomical object, most likely. I think probably pre-humans could look at the sun and note it in some sense. And it's, scientifically speaking, something you may or may not know, it's sort of academically isolated from the rest of astronomy quite a lot. So I'm in a math department, and that's very common in the UK, and where people who study the sun are oftentimes mathematicians who do other things as well. And the reason is we know so much about it, and as a result of that, we do a lot of mathematical modeling. That is very different kind of mathematics that you usually see in astronomy. Astronomy is certainly not short on mathematics of any kind, but it's usually a very different style. So I didn't know really what to pitch, and I'm going to say things that are like what my colleagues tend to find very interesting because they don't know about them very much, which is a very kind of common astronomical sort of style of doing science. Basically, my professional opinion is that people who study the sun should act more like astronomers used to. rather than modern computational mathematicians, as you're supposed to. So this is the Aztec sunstone. This is just, a hint that people have been culturally obsessed with the sun for a very long time, of course. This isn't even that old. It's actually quite a lot was going on in Edinburgh when this stone was carved in the 1500s. So it is written in the star. I think you probably get the star. We're obsessed with the star. It's cultural. It's everywhere, right? You can't avoid it. And it's even, you don't even realize it, right? I want you to pay attention, the Daily Star and obviously the sun, there they are. So it's obviously in pop culture, right? So we have songs about the sun, Tequila Sunrise, Here Comes the Sun, Day in the Sun. But then there's the police, I have to say, really they hit it. There's a little black spot on the sun today. So Sting was thinking deeper about sunspots. And of course there's, this Japanese flag, which is the rising sun. So people, this is just cultural, to remind you that the sun is a pretty big deal. And does anybody know where this is? I expect somebody in this audience knows what this is. Newgrange, right? Yeah, so this isn't very far from where we are. This is in Ireland. And I like to make the point that this is probably the oldest dedicated solar observatory in the world. Nobody's know for sure what they use it for, but if you don't know what this is a tomb in Ireland. It's about 50 meters across, so it's big. And there's a passageway, there's a passage tomb, there's a passageway that goes down the middle to the center. And every year on the solstice, the sun shines straight down the corridor and shines on the back, on the stone back there. And you could think, okay, this is ritualistic and whatnot. I was just today, my son, Roman, hi if you're listening, he insisted we go to see Camera Obscura, and I hadn't seen it yet. Fantastic, I'm sure many of you have seen it. I've never seen a proper Camera Obscura before, but I'm pretty certain that this would have acted as a Camera Obscura as well. And so they probably would have seen sunspots when they were active, and they were probably doing this for many, many years, and so they probably would have seen that the spots had a cycle, and they wouldn't have known why, or they wouldn't have known what they were, but they probably 5,000 years ago were observing sunspot cycles, is in my opinion. Okay, so really actually a really dedicated observatory. And of course, this is again, not unique. This is, does anybody know where this is? I doubt it. Yeah, so this is in New Mexico. This is called Pueblo Bonito. This is in Chaco Canyon. And this is another society that lived about 1,000 years ago. And that long wall, is maybe about 200 meters long. And it's perfectly aligned with the location of the sunset on the solstice. Except for that drift, so it's more complicated than that, but basically it's more or less aligned with that. So these were people who observed the sun, and they had their own sort of sunstones that on the summer solstice, there would be this spiral. This was up high on a cliff, and the sun would come along there. So this was probably not observing sunspots, but it's still obsessions with the sun, right? Now, okay, so that's just a bit of background, of course. The modern scientific observation of the sun, proper telescopic observations, happened just after the advent of the telescope, right? So Galileo essentially invented telescopic astronomy, and in 1612, around the time that many of the buildings in this neighborhood were built, not many, some of them, he pointed at the stars, right? So you probably are, being astronomy enthusiasts, have seen perhaps a replica of Galileo's telescope, but if you haven't, it's pretty interesting, right? It's about 1 inch in diameter. It's about this long. It's got a hole that's hardly a couple millimeters. You got to peek through it. And he wrote this fabulous book called On Sunspots. And he made these amazing drawings over the course of, we have them at least over the course of a couple weeks. This is one of them. I don't know if any of you have seen these before. This is some of my favorite. You can turn these into a movie. And you can show that, what you can know by just this simple observation, right? So we know now that the sun rotates and it's tilted on its axis, right? 23 degrees or something like this, right? And what I find absolutely incredible is that Galileo got it right. He couldn't have cheated, right? Nowadays, it's hard to forget how easy it is to cheat and Google something or whatnot. I mean, not unethical cheating, but you know what I mean. He was just drawing what he saw, and if you look closely, you can find these images at Rice University has a website. Just Google for it, cheat, and you will see images later on that I'll show of close-up sunspots, and he really nailed it. I mean, you have these dark cores with its filamentary surroundings called sort of dark umbra and filamentary penumbra, and they come in groups and pairs, and in fact, he did a lot better than a lot of his contemporaries. I'll mention that in a minute here. So I'm just absolutely astounded by how good this was. And of course, he didn't look at the sun. He would have projected these onto the floor and then, or some sort of a camera obscura perhaps, and would just draw what he saw. I think Galileo was probably, like Leonardo, had the advantage of being a really good artist, and that also just shows how various other kinds of skills really play into the ability to make accurate scientific discoveries. Okay, so this is now zooming quite a bit forward in time. So again, I'm going to give a bit of a history here, and you may know some of the history. You certainly will know some of the characters. And I do so because, again, I want to make the point. I make these points to my colleagues to say that we should be noting kind of old-fashioned observations more than we often do, and sort of laying evidence kind of out in front of us. So Walter Maunder, another really incredible character, gave an address to the Royal Astronomical Society in 1920, and he said, in this sort of muscular prose, the Royal Astronomical Society was founded in 1820. At that date, it was known that there was a sun, that sometimes there were spots upon its surface, that the sun rotated on its axis. Practically, that was all. So that's basically what Galileo had in his drawings, right? And he then proceeded to lay out a lot more than was known at the time, of course. So this was a very important lecture. More was known before this time as well, which I'll mention. But this is kind of I could rephrase this, and occasionally I should have done it. I have kind of a cheeky sort of Victorian-sounding version, which is sort of like, Walter Maunder addressed the Royal Astronomical Society in 1820, and at that date it was known that there were, that spots were magnetic, and so on and so forth. But practically that was all. And we still really don't have a lot more factual information than this, really. I mean, in some ways. I can put most of it in this presentation. Here's some more early papers. This is, again, I apologize for the words, but I just like these things. So there was a German Schwabe in the 1850s, and then Carrington, who was a really well-known character, and they were writing their first observations, more detailed of sunspots and how they behaved dynamically. A point I like to make about this, and this should be really apparent living in Edinburgh, right? I mean, this was happening contemporary with Maxwell. He was doing electricity and magnetism, and people were inventing thermodynamics. And this was before relativity, quantum mechanics, and Big Bang cosmology were even kind of on the horizon. And all of the things that these observations were occurring before that, all of these things were needed to subsequently understand what we now know, right? So we know about how spectra works, we know about how the sun burns, we know about nuclear physics and those kind of things. So we've learned an awful lot by these things, but we are actually still stuck on these pesky sunspots, right? So no, I will here to tell you, kind of spoiler, we don't know how sunspots happen. People will claim they do. They're all overstating it at best. And I have my suspicions, but again, I will not tell you that I know how it works, right? So all the revolutions of modern science have come and gone, and we're still stuck on these sunspots, which is why I think it's really fun. Also, in these words, and again, I say, go back and look at the old papers that really love doing it. You'll find these incredible little gems. I'll read it here on my screen. This shows you how different of a time it was. You can't do this now when you write a scientific paper. Some of you may have done a scientific paper yourself at some point. You can't apologize in the intro for why I didn't have more papers for you, right? So I had fully hoped by the time the society would meet again, I should have been able to present members with a taller, more complete discussion of a series of sunspot observations. But a family loss at the hand of death, so sorry, I was busy. Again, it just shows you how the whole world can change, and we're still stuck on these sunspots, right? But these are Carrington's drawings from those observations, and you can see that he had a lot better magnification than Galileo. But I will ask you, perhaps I'll even take a poll, and maybe you haven't studied Galileo's drawings, but my opinion, this is not as accurate as what Galileo was drawing 300 years before. These are good, but these are blobby. They miss actually quite a lot of important features. Okay, so I lived in Australia for 10 years before I was in Edinburgh, and I agree, this kid has it figured out. How would you make any place a better place? More magnets. Okay, so this came out of the newspaper while we were in Australia at some point. More magnets, I agree. So we now know that sunspots are magnetic. Okay, so they're Galileo at the time didn't have any idea. He speculated that they were maybe in front of the sun. He didn't, or people speculated that they might be fires burning on the surface of the sun, and there was smoke from fires. Right? Some people said it was spirits. Well, in the early 1900s, not that long ago, really, George Hale figured out on the probable existence of magnetic field in sunspots. And magnetic fields are why sunspots happen in some sense, but we don't know why the magnetic fields happen is the issue. And George Hale was another incredible character. Many of you may know who he was. So he had the wonderful pleasure of founding Mount Wilson Observatory, which is in California. Looks quite like quite picturesque place to just sit and look at the sky. And he basically used a technique called Zeeman splitting, which you may or may not know about, but it's spectroscopy. And this is him scouting it, right? So in 1903, he went up there. He was a rugged individual, and he went and he tromped around and found the site. And you may know Mount Wilson for another reason, that this is where Hubble was doing his important work on extragalactic nebula, figuring out how the scale of the universe and cosmology, Big Bang cosmology, right, was a result of those pesky sunspots. So there's more connections. But Hale was not interested in that. He was interested in these sunspots, and he made these beautiful images, which are now actual, not hand-drawn images, but are actual sort of, which we would call photographs of some kind. And now these are really looking a lot like what we see today. But I don't know if you know the history of this. He was an absolutely fascinating character for many reasons. Again, he invented the spectroheliograph when he was an undergraduate at MIT. And so Zeeman, the Zeeman effect, where light is altered, the spectrum of light is altered by magnetic field, was sort of given the second Nobel Prize in 1902 to Zeeman. So this was a new effect, and in the 1880s, sometime around the discovery of the Zeeman effect, he decided to do this, and as an undergrad. And I don't know really how it happened, but I have a lot of imagination about how that could have happened. But look, I'm at the universities, I encounter a lot of undergraduates today. I don't encounter any undergraduates that build their own spectrograph without getting permission. And I think this is another thing that I think we've lost. I don't know, I don't want to be golden age thinking about it, but it's, I think back then in those days, there was a lot of not asking permission for things, right? You had the confidence. I think there's plenty of people today who are clever enough to do such a thing, but I don't know that there's many that are confident enough. And again, that other image of him, right there kind of shows it as well, right? So, he was a multi-talented individual. So he built a spectrograph. He did this for his undergraduate thesis in the 1880s. And then this also shows you another fact, perseverance. So Hale finally made his publication sometime between 1908 and 1913. So it took him, so he had the spark of an idea when he was an undergraduate. He went and did the politics and the finances and whatever else it took to go, and the physical exertion to go tromp around and build Mount Wilson, and then lots of hard science to basically go and prove it. So it was, a multi-decade journey on his part. And he found various laws. Something we don't have enough of now are qualitative laws. We have a lot of data, and people talk about AI, doing things for you, but we don't kind of distill it enough into something you can just sort of say. But he did, and he found that sunspots tend to come in pairs with opposite polarity. And in the northern hemisphere, let's say at a particular cycle, the positive polarity will be leading the negative polarity. So this is magnetic field poking out of the sun versus poking in, for example. And then in the southern hemisphere, it'll be reversed, right? So you'll have the negative. So this is implying two sort of bands of magnetic field that are wrapping around in opposite directions in the sun. So you can, again, you can sort of observe a lot by looking. So back to Maunder. So in this lecture, he went on to introduce some data. This is another just incredible observation that just shows you what it took. And you're no stranger to this stuff. I mean, I'm sure you all have heard of dozens of astronomical discoveries that took this kind of length of time to put together. But he published a paper in 1922, and this is what is called the butterfly diagram. And what did he do? He went out every day, and he looked at the sun, and he found where there were sunspots, and he noted where they were in latitude. And this is a diagram in time going along the bottom, and we have latitude going up and down. And he just made a tick mark if there was a sunspot there at that particular time. And you can see that this is the solar cycle laid out for you. This is the roughly 11-year, one of those butterflies is about 11 years of time, going from 1874 to 1913, 3 of them. And again, just imagine what this would have felt like to do that, right? You would, after 2 years, you would just see these 2 splotches. And then after 5 years, you would see kind of a big lump. And you're like, okay, I don't know, what is that? Is it going to keep, you would have no idea. And then you'd say, okay, well, oh my God, it appears up north again. Okay, well, weird, right? You do it again. Okay, that's 2 things that look similar, and you watch it a 3rd time to be sure, right? And I just imagine this playing out, in slow motion this way. And then, of course, given the war, he had to wait to publish the work as well. So it just shows you what, and this is just one of the most monumental observations that there ever was. And we don't know why this happens, okay? So we don't know why this happens. Some people will claim they do, but they don't. We don't know why it happens. And then it turns out, once you know something is happening, you can go and find more evidence of it, and we now know that the sunspot cycle has been influencing us forever and ever. So you can go back and look at data in tree rings, which are influenced by cosmic rays, and you can actually look at direct sources. So Galileo observed things in the early 1600s, and then sunspots basically stopped happening. And he actually got bored and thought, well, okay, I'll move on. But other people kept it up and didn't see anything. So they were constantly looking, but not finding. And then this thing's happened again a couple times. There was something called the Dalton minimum. The Dalton minimum happened in the early 1800s, and there was an interesting, I took a slide out, but I'll mention it in a minute. And again, there's something, and just also to tell you what you can observe by looking. I've been seeing this kind of a diagram for 20-something years now. And only about a year ago did I notice something that I had never seen before. So again, this is latitude here. Down the middle is the equator. And when we came out of what's called the Maunder minimum, where there were no sunspots for 80 years, all of the magnetic field was in the southern hemisphere for some reason or another. So there was a giant asymmetry. It turns out about 5 years ago, I wrote a paper about how a star, not the sun, could have a dynamo only in one hemisphere, and I didn't even know that the sun is doing that, right? So the right hand doesn't know what the left hand is doing off of time. And you can see all this kind of beautiful modulation, and I would say anybody who ever just sort of gives a full description of how the magnetic dynamo works will have to explain everything you see here, roughly speaking. Not all the details, but why does it modulate? Why does it get sort of periods of big? Why does it go away? Why do you get the asymmetries? Yeah, so what does it all mean? And one of the things is why the solar physics is very different than, dynamo theory is very different than other kind of astronomy, is it's a lot more like biology. It really is sort of like, this could be a picture of the population of some beetle or something like that, right? And you would have to say, well, why do the beetles have these population crashes, right? And so it's a very different kind of science. So you may know that the sunspot cycle influences climate. So at least people believe it does. This is kind of controversial still, but probably is true. So during the Maunder Minimum, it was cold. This is the Thames. They used to have these Thames frost fairs, and everybody here probably knows that London does not look like that in the wintertime very often. But it did back then all the time, and they had kind of festivals out there all the time. And then the Dalton Minimum, where this happened in the early 1800s, there was the Year Without a Summer, for example, which was 1815. And that was partially the eruption of Tambora, the big volcano, but it also coincided with this, and for that we have Frankenstein, right? So Mary Shelley was holed up in a castle and riding with Lord Byron. Okay, so another thing that Maunder just kind of noted by just, again, lots of careful observation, is that if you look at sunspots near the equator, when they happen to be near the equator, they are drifting faster than the ones that are up higher latitude. So there's a shear that things seem, the motion where things are flowing kind of in a jet going around the equator, and then the poles are moving sort of backwards, relatively speaking. Yes. So what was I going to say about that? Oh, yes. One thing I forgot to mention. So in the butterfly diagram, I forgot to say that drift, the sunspots themselves are not actually moving very much. The sunspots pop up. They live for about a month or two. That's one solar rotation, roughly speaking, and then they kind of get broken apart. Okay, so it's not where the sunspots are not moving themselves. It's the location at where they're moving is migrating. Okay, so it's a migration of sunspot emergence, not sunspots themselves. Okay, so flows indicate really cool things with magnetism, basically. So this is, you can now know about magnetic induction. This is things that go back to Faraday and things like this, right? So this is a YouTube video. Nope, that doesn't work. Shucks. It was working when I was doing it before, but this is an embedded YouTube video. Huh, darn. Let me see if I just exit. Oh, I'm not on the internet, that's why. Does that work? No, it's not working. I apologize for that. I need to be on the internet. This is a YouTube video. The point is you take a copper pipe. It's a really cool thing. Go Google it. You take a copper pipe, you drop a heavy magnet through it. As the magnet falls by gravity, it induces currents in the copper pipe, the highly conducting pipe. And those currents induce magnetic fields that react back on the falling motion of the magnet itself. So you can drop it through and it just looks like it kind of, like it's falling through sludge, right? And it's just a really, really dramatic effect. And this is what happens. So now you have fluid pushing blobs, like highly conducting blobs, through other fluid and dragging magnetic fields along with it. What that does is that stretches and amplifies things and can turn a dynamo, basically. A dynamo being, kind of the amplification of magnetic field by kinetic motions. So there's other things you can say that, in the interest of time, I won't go on to, but it's not a fossil. It's not just sitting there as a fossil magnetic field. It's not a permanent magnet. It also flips its polarity. And finally, the final piece of the puzzle was in the mid 20th century, where Babcock, a scientist called Babcock, figured out that there's a big dipole magnet that basically goes along and flips itself over and over again with each cycle, right? So this is kind of the final piece of the what. Okay, so the how, we still don't really have anything much more to say about it. So that's the old days. Now let's get into more modern times. I probably should try to hurry up a bit. So these are the kind of satellites that we now look at. These are 3 examples of them. So you take the sun. Here's the whole disk sun. I like this image again because I can't help myself. There's a little spot up there. Can anybody see it? Does anybody know what it is? ISS and the space shuttle. So this was you know when this was taken. So this is a space shuttle that was like just leading the ISS. But anyway, this is roughly to scale. This is how big a sunspot is roughly, and you pick a spot. This wasn't on that particular image. I superimposed it, but if you zoom in, you can now finally, there you are, get a decent up close of a sunspot, and it's sitting in this roiling, turbulent convection of motions that are pushing the magnetic field through this thing. And you really see Galileo got it right. I mean, this is at least why I say. You see these dark umbral cores and these penumbra, what's called evershed flow. There's super hypersonic flow coming out of these things. One of these little granules is the size of the UK. Actually, you can see there's Europe for scale. And the flows are coming up and flowing out and going back down again in about 5 minutes. So just imagine how fast you need to be flowing from the middle of the UK to London and back, basically in 5 minutes. So very, very fast. There's really more what's. We're finding more what's all the time. This is the first time in 2006 when somebody ever witnessed the birth of a sunspot in real time. I was a student, PhD student at the time, and I had been staring at this since 2006, and I don't know what's happening. Nobody else does either, right? So, I mean, this is a real puzzle, because if you take a bunch of magnets in a tray and you flip them to like little wafers, and then you flip the polarities to be positive and negative, opposite polarity magnets will repel each other from the sides. So if you put them in a tray and then you put a lid on it and you shake them, they'll all just mix up like salt and pepper. Okay, they will not clump together. The ones of the, sorry, not opposite polarity. Same polarity magnets will repel from the side. So they don't want to clump together. They want to repel from each other and mix up as much as possible. But some force of some kind has to be responsible for clumping these things, and nobody really knows what that is. I mean, people have names for this called like the negative pressure instability, but that's like saying dark matter. I mean, it's sort of like saying dark energy. It just is a name that says this. So then here's a big kind of conceptual big picture of a single solar cycle from 96 to 2006 or so. And we are now living in a time where the sun is active roughly like it is in the middle, right? So we're roughly 22 years ahead of this, roughly speaking. We're a little early, I think well, no, actually we're probably near solar maximum right now. And then the image that I sent to sort of advertise this talk, NASA took 10 years worth of images and stacked them on top of each other. And you can start to see, again, this is meant to just be beautiful. I really think it is, but it also tells you a lot about what is happening, right? This is telling you there's 2 big straps of magnetism that wind themselves around. Hale figured out that one of them will be tending to go that direction. The other one will be tending to wrap around the other direction. And that they don't tend to want to get too close to each other near the equator for some reason. Okay, so these are clues. And of course, this is important. One of the nice things about, I've known biologists who say they like to work with doctors, collaborate with doctors, not because they care about solving medical problems, because they just want to be kept honest. That doing solar astronomy or solar physics is great to think about what actually happens. There's the Earth for scale. I don't know if you can see it. So the sun, these things erupt sometimes and send 1 billion tons of million-degree plasma our way. Pretty serious when that happens. This is from back in 2003 when things were pretty active. And again, so there's the occulting disk, which is the big disk in the center, and then there's a smaller circle, that's the size of the sun, so you can get a sense of scale. And I just showed you the size of the Earth, roughly speaking. And then boom, these satellites are getting pummeled by this stuff. And we would be too as well. So we need to worry about these things as well. Of course, as you all know, there's some benefits to all of these things in the form of Aurora Borealis. But my partner's Canadian, actually. She remembers this happening back in the 80s. One of these storms knocked out power to several million Canadians for a couple weeks. Even I was just Googling in preparation for this talk, Lloyd's of London, just as of March this year, commented, and they've done this before, said that that they estimate currently $2 trillion worth of risk associated with solar storms per year, and then they will say, like, the biggest threat to our way of life on Earth is the sun, basically. So people don't really realize this, that we could be set back to year zero tomorrow, right? Or next week. That's the other cool thing about it, right? I mean, we've all went through the pandemic, and we kind of know how life can get turned upside down very quickly. But this could be the opening scene of a science fiction movie, right? So, so it's worth actually thinking about how these things happen. Okay, so that is like everything on the outside, and a couple more minutes, I think. So now let's lift up the hood and look at the inside a little bit more. So the sun is a star, and some of you may know what a star is, more than I do even, but it's nuclear burning in the center. And the sun is a middle, sort of low to mid-mass star, and it has a radiative zone where energy is just kind of leaking out very slowly, taking 100,000 to 1 million years to sort of wander its way out of the inner 70%. And then once you get to the outer 30%, that process doesn't happen well enough. And this is now where you start to get that roiling, boiling, turbulent motion that you saw on the surface, okay? And this is a picture from National Geographic a few years back, probably 20 years ago. And it depicts sort of these giant sort of rolling circular motions indicating that things are rising buoyantly and then depositing their energy outward in the convection zone. All right, so people who, like myself, who studied in solar interior were usually obsessed with the convection zone. There's a little side note. I wrote a paper a few years ago. There's this thing called the convective conundrum, wondering like what kind of shape the convection takes. Is it sort of big and blobby like the thing on the top, or is it small and cylindrical? And essentially rotation affects things quite a lot. So the sun is also rotating. It takes about a month to go around. And that affects things quite significantly and leads to really interesting consequences. So I wrote this paper, and then it turns out the media had a bit of fun with it. The Daily Star, in fact, right? And this was like my proudest achievement. Team of boffins. I'm a boffin. This is the first time I was ever called that. And Forbes picked this up, and cigars, because they're cigar-shaped columns. May account for strange solar strengths as sun shoots flares. This is completely bollocks, but it's still fun. The Daily Star actually didn't do a bad job. They could have done worse. So anyway, so it's still a cultural relevant, I suppose. How do we know what happens inside of the sun? This is just an area I could go on and on and on about. None of this up to this point, except for the cigars, is my work. Leighton, Simon, and Noyes. This is interesting. I like the names. Leighton was a good friend of Richard Feynman, who wrote the Feynman Lectures in Physics together. Noyes is somebody who studied sound in the sun, and whose name was Noyes. Other than that, I don't know anything about him. And then Simon, I helped install his software on his Mac computer like 25 years ago, when he was retired and had just bought a new Macintosh computer. So he was an old man when I met him, a really nice guy. But you can just look at so I told you these blobs are taking about 5 minutes or so to turn themselves over again. That 5 minutes is leading to this kind of constant pummeling on a 5-minute sort of interval. And so if you take a small patch and you look, it sort of looks random, But if you just look at a given location, you can see these wiggles, and those wiggles have a characteristic wiggleness to them, right? So, which is about 5 minutes or so. And it turns out that these are actually acoustic waves that are bouncing around inside of the sun, and they burrow their way inward and come back out again, and they carry information about what's going on deeper down. And you can do inversion of those, you can do seismology, just the way we do for the Earth with earthquakes. But it's actually way better because there's loudspeakers just constantly going at the surface, basically. And don't worry too much about what these are. It would take a minute to explain, even to somebody who already knew. But the point is you can make an observation of a picture like this, and you can calculate a theoretical picture like this, and you can look at the differences of those and use those to infer what's going on inside, right? So the differences between these two pictures is enough to sort of work out what the flows are like, what the temperatures are like, and so on. So another thing I'd like to mention about science in general is a analytical calculation is a potential observation, right? If I have a formula for something, then I can plug that something into that formula on the right-hand side, calculate something on the left-hand side, and match the left-hand side to something I measure, and then jiggle the other thing I put in to figure out what it really is, right? So a formula is a beautiful thing. This is how spectrographs work. This is how microphones work, right? I mean, all of these things that we use and we just consider are ultimately formulas that somebody's derived at some point. This slide is kind of out of order actually, but I've said that this slide is out of order. This is the thing that should be first. People use this to measure a picture. We know way more about the inside of the sun than we do about the inside of the Earth in some ways. This is a picture of the rotation velocity, the angular rotation velocity of the fluid inside of the sun as a function of latitude and depth. So inside the sun, it's all moving roughly together like a solid body, and it's sort of all the yellow in the inner 70%. At the equator, it's a big, fast jet moving around, and at the pole, sort of is a cap that's going backwards. And this is the thing we as theorists just use all the time to basically say, whatever magnetism is doing, this is what's causing it. Okay, this is the induction effect. And I said this for many years, that this is really worthy of a Nobel Prize in my mind, like no doubt. I never thought that it would achieve something like a Nobel Prize, but it was awarded the Crawford Prize, which is kind of a decent substitute in 2004, last year. And I know these people, actually. They're people I've known for quite a long time, and extremely well deserved. Douglas Goff is a professor emeritus in Cambridge, and Georg Dalgaard is in Denmark, and Connie Arks is in Denmark as well, I think. How much time do we have? 5 to 10 minutes? Okay, great. So there's two big layers here. The tachocline, which is this shear zone where things are moving past each other. Anytime you have fluid moving past other fluid, has potential to stretch magnetism out, to do something. And then there's the near surface region as well. And the tachocline has been the object of most conventional sort of studies up until this point. And I won't have time to really go into much detail. My latest work has been pointing out that I think the surface is a lot more important than people have anticipated. So this is kind of a conceptual model of what things have been going for 20 years or so. I don't expect you to follow. This is just for intimidation. And the point of it is that it's Rube Goldberg, right? It's a lot of things need to feed into other things. And when you go and look at every part of it, it just hasn't ever worked the way people thought it would. So I just like to do this and cross it out and say, let's move on. And so now I'll tell you very, very briefly about some of the things that I'm working on. I have a couple projects, scratching up the furniture. So about a year ago, almost now, I and my friends wrote a paper that, very fun, got on the cover of Nature, saying that the solar dynamo begins near the surface. This title has really irked my colleagues because it's so declarative, but I didn't pick it. The editors require you to pick something very declarative that'll really irk your colleagues. So it's been kind of fun. It's been quite fun, and this image ended up on the cover. And I really don't have time to tell you about why I think this. I guess I can go very, very briefly and mention one or two things. But there are, and then they did a follow-up. They had another expert also write something that said an instability that we identified could be the reason. This, of course, got some press, and I might have been called a boffin again. I'll just say, like, one of the reasons why I did this study was to sort of maybe bring it back to something I said at the beginning, is that I believe that just like looking and placing clues on a table and rearranging the cards in the right order may be a way that the crazy detective does in the story with all the strings and stuff maybe, but helps. Like, so this is an image that led a lot of people were only looking at visible light. And you see these little dots, and let's just say, maybe it's a long story, but you can imagine these little dots as strings that are getting pulled up from down below. But if you look at a magnetogram, you just see this stuff just sitting there like a submarine lurking right below the surface and not doing much. Okay, so these spots are sort of local pimples, if you want, of some kind of like periscopes of some submarine that are sitting right below. And yeah, and it sort of seems sort of shallow and persistent. And then this is, you can not only measure the flows under the surface as sort of a time average, but you can measure them in a time-dependent way. And you can see that there's a pattern that begins at the beginning of the solar cycle near the surface and penetrates its way inward. So again, I'm going quite quickly through these. This I'll have to just skip. This is fun, but this is that instability. It relates to other things that happen in accretion disks. And we did some calculations of this stuff. So I'll tell you something else here. Yeah, so basically now this is what I do a lot. I run a project with my friends called Daedalus, which we write software to do calculations, simulations of things with fluid dynamics that happen in astrophysical settings and oceanographic settings and other things. And we've used it for carbon burning fronts in other kinds of stars, or simulating equatorial waves in the ocean, or magnetohydrodynamic shocks and various things. So this is a massive star simulation, which would be like a 10 solar mass star, for example, which is kind of inverted version of the sun. People have used Daedalus to make images. People working with Pixar have used Daedalus to make these blobs. It's quite fun. And then I'm now currently working on a project to model what's sort of little going on at the cores of sunspots. All right, so you have in these little umbral dots, they're called. You can see these bright points, and I have some model for why that might be happening, and we can run a calculation using the software. So this is what I say. I'm a mathematician. A lot of my time is spent designing the software and the algorithms to do these kind of things, not looking at the sun per se. But we ran a calculation, and we found a mode, an eigenmode, if you know what that is, or a pattern, if you want, to just be more simple about it, by just simulating the equations that govern the sun. And they have certain characteristics in common with the patterns that are observed. They're not perfect. There's a long story here. There's other patterns that are, again, also correlate with the patterns that are observed. These were sort of a confirmation of kind of a chain of reasoning that we had sort of laid out. But then, as a rule of thumb, just doing a calculation is so by some people consider it enough. I don't. I want a really good sort of on fingers understanding of it. So again, if you needed a bigger computer, you need a bigger think. Or sort of Occam's razor. The best model for a cat is a cat, or preferably the same cat. And again, I could go on about what this slide means more, but the point is I was able to make a simple enough model that's very similar to the dynamics of an elastic buckling beam. That buckling beam, I was gonna I had my magnets. I keep forgetting to bring my magnets. I've got a bunch of hematite magnets. You've seen them, you can go buy them at Dynamic Earth or something like this, right? And And magnetism and elastodynamics, elastic solids, are actually quite a lot more like each other than you think. So if you take a bunch of marbles and try to stack them on top of each other, they'll all fall over the place, right? That's buoyancy, that's gravity pulling heavy things down. But if they're magnetized, you can stack a bunch of them together and it's no problem, and you can jiggle it and it'll stay together a bit, and if you press on it hard enough, it'll go shooting all over the place. And it turns out that that's the magnetic field adds a rigidity to the column, and so it not only do you make magnetism by pulling on it, it springs back on you in the same way a buckling sort of sheet will do. So this was a model that was analogous to what was happening in the sun. So there's an analogy there to say that buckling beams and like this magnetism has some relation, very, very complicated to get from one to the other, but you can get there. There's other analogies that are actually as well. So if two things are analogous, there may be a third thing that's analogous. So you can also think of a bunch of skaters on a track, and they flex the track as they go, and then they all kind of collect in the center, and then But the beauty of this was that you could use this mathematical model, this simple mathematical model, to generate an algebraic formula. So remember what I said about formulas. Right? This is not the greatest formula in the world. It's kind of messy, but it's a simple algebraic formula you can plug numbers into. And it was now something on the right side of the equation that we knew, and something on the left side of the equation that we don't know. And we have a measurement which says that this number should be roughly 1 in some units. And we could plug everything in, roughly speaking, with lots of uncertainties. And we know those numbers, there they are. It turns out that it happened. I didn't rig it that way. And you get a number which says that this number should be about, with this really ridiculously oversimplified calculation, should be 6 nanohertz, 6 times 10 to the minus 9. And the actual number is about 3 times 10 to the minus 9, happening, millions of miles away, and right. And this is about little dynamic. So this is an indication that we were on the right track, right? So this number matching was one of my happiest moments, I would say. So this is where I am at with these things. 6 happens to be 42 over 7, and it makes you stop and think. Kind of makes you stop and think, doesn't it? So normally this would be where I'll leave it, but I'll leave it actually with the star of the show.
Thank you, that's really good. We've probably got time for just a couple of questions. If anyone's got any questions, I can't see. Oh, I did want to.
I'm also happy to hang around afterwards and talk to anybody.
Thank you for an excellent talk.
Thank you.
We often do solar observing when we can see the sun as part of an outreach activity. And one of the questions we often get asked is what causes the sunspots, and we glibly say magnetic fields. Are we wrong?
No, that's the best answer anybody can give, I think. You obviously can waffle more.
We do.
Yeah.
With our hands and
but really, that's about the best honest answer you can give. You can say more there's more that you can say. Why are they dark? That's actually known, and it's good. So magnetic field, as I explained, adds rigidity to the fluid, and convection, boiling sort of motion, needs to move things out of the way. And the magnetic field, basically, it's like adding wires, like rigid structures going down through the fluid, which inhibits the heat transport coming up. And because it's less heat transport, it's darker. So that's why they're black. Is that and you can actually see this with these umbral dots, are these bright points where the magnetic field is moved out of the way, and you're looking down into a hotter underneath, and it's brighter there. So if you want to elaborate, you can say that it inhibits the transport of the heat coming up. And the reason why it seems to do this, I mean, people have guesses, and it has to be sort of, what I'm about to say sort of has to be true, that it's sort of a negotiation. And the magnetic field says, okay, we'll kind of all come together, which we don't like to do. but it'll allow the convection to go on by itself, uninhibited, and we'll be uninhibited by the convection. And so it's this kind of like a compromise in energy. So it clumps together for some reason because it wants to get out of the way of the turbulent motion, and then it causes less turbulence there, hence darker. Sunspots, by the way, you may or may not know this, they look dark, but they're actually as bright, roughly speaking, as the full moon. So if it was just sitting on the sky by itself, it'd be painful to look at, but it wouldn't be dangerous, I guess. But they are quite bright still, but relatively speaking, not as much.
Thank you. Probably just time for one more. You get to talk next.
Sorry. Thanks for the talk. Are there any new types of measurements you'd like to see being done on the sun that would help get you additional data?
That's a great question. That's a fantastic question. There's a lot of people who are still doing a lot of measurements, and I like the data that's coming out. There's new solar probes, there's space-based probes, there's no shortage of data and instruments looking at, and I'm not really knowledgeable enough and creative enough to know about instrumentation to know what I want. What I really want, and I actually think amateurs could do this quite effectively, is the people who tend to collect this data tend to just give it to you in a fire hose, and they will interpret it in a very sort of obtuse way. What we really need more of are the kind of old-fashioned laws, like kind of rules of thumb, qualitative distillations of all of the data into, sunspots tend to trail each other. And there's more of them that exist that I didn't mention. They tend to be a little bit of tilt. There's another law called the hemispherical helicity law, but these qualitative laws that, patterns, like this is what we need. This is what we would crack, what would give a clue if you want. So yeah, take as much data as you want and just look at it with an eye more along the lines of what people would have 100 years ago, rather than they kind of commonly do today.
Well, also, we could carry on asking questions for us, so chat to Geoff afterwards. We do the outreach on Blackfoot Hill, so if you want to come up and explain to people at Doors Open Day, then you probably do it better than we do anyway. So thank you very much. Thank you.
Thank you.
Some.
Good evening, everybody. So the first thing I've realized when you're doing a PowerPoint presentation on the sky in summer is never follow a mathematician that studies solar physics, because this is going to be comparing sort of comparison could be hard, let's just put it like that, so be kind to me. So it's lovely to be back, actually, for those of you. I won't bore people, but I've been off for a while, an unenforced absence, so it's nice to be back. So yeah, the sky in the summer of 2025. I don't know if any of you have ever had this experience. I've often had very odd looks on aircraft at night when I've had either a coat or some other blanket over my head pressed against the window, and someone thinks, am I wrong? Am I trying to bring down the aircraft? When actually all I'm trying to do is photograph Venus on my mobile phone. So yeah, that's a regular occurrence. So just briefly, what am I going to go through? I'll cover roughly what the skies are doing in Scotland in the summer. Not much is the answer, but we'll try and stretch it out. Embarrassingly, I'm going to say something about the sun. Very little, as it turns out, because I don't think I could add more than what's already been given to you. The moon, the planets, the stars, obviously, and then with that I will end. So yeah, living in Scotland in the summer, what a challenge it is when it comes to observing the sky. Never an easy thing. You can see the graph online there, roughly where we are today. Obviously, we no longer have nighttime in our sky here in Edinburgh, neither do we have astronomical twilight. At the moment, we're stuck in the nautical twilight zone. But that presents its own challenges, obviously, when you're doing some amateur astronomy. Can I highly recommend, both for members and non-members, that you look at the excellent Sky Diary on the ASE website. I think it's probably Mark who maintains it, but it draws in data from professional websites. It's brilliant. A lot of my talk has been ruthlessly plagiarized from it tonight. So please don't, if you get a sense of deja vu, you look at it, you'll know why, but you heard it from me here first. Yeah, it's a really good website and very useful. So the month of June, well, obviously the sky in June is challenging, but thankfully the Sky Diary online on the website here gives you quite a good rundown on things you can do in June. I'm not going to go through all of these, or we'd be here until June of next year. But I'm going to pick one, which is on the 19th of this month, which you can see is the close approach of the Moon, Saturn and Neptune in our sky. So this is going to happen just before dawn. Well, at the moment, everything is before dawn if you live in Scotland at this time of year. But if you look, if you're looking east around 2:30 a.m. on the 19th, you'll see the last quarter moon. It'll be about 9 degrees above the horizon. Its magnitude at that stage is around -11. Neptune is actually also in the neighbourhood. It's about 8 degrees above, and it's about magnitude magnitude 7 rather, which is quite challenging. And Saturn is also rising in the east. So for those of you who are interested in astrophotography, maybe that's something you'd like to have a pop at. I'm not that skilled, but many people in this society are. Moving on to July, well, again, as I said, the website, the ASE website tells you all you want to know and more, quite frankly. But I've just picked out one item here, which is on the 20th of July, which is a close approach of the Moon and M45, better known as Pleiades, in Taurus. Venus, as you'll see, is also making an appearance in the mornings now, or at least it will be by July, and I'll speak about that. Yeah, it's a nice object if you're looking to. There it is, just to highlight. If you're looking, if you're up that early, quite frankly, and you want to photograph something nice, well, then it's in the eastern sky before dawn. Around about 3:30 is probably best. After that, it's getting, it will get lost in the dawn. It will get lost in the dawn glare. And also, the crescent moon will have a conjunction with Venus the following morning, again around 3:45 in the morning, looking east. It's always difficult at this time of year. But just to add a sweetener to this, when you look more closely, you'll see Uranus is actually also in shot. This is taken from Solarium. But if you want to try your hand at the real thing when it comes to the 20th of July, well, then I'm sure it will find a place of honour on our ASE Flickr page. August, August we're starting to get back to slightly easier times, in the sense that we have a return of actual night time, only about 20 minutes of it, but at least it's something. But there's lots of events happening in August. Obviously, the Perseid meteor shower is always a big favourite for people in August, and I'll refer to that later. But the one I'm actually going to talk about just now is also on the 12th, which is a conjunction between Venus and Jupiter in the early morning sky, which really should be quite a spectacular thing to see. Obviously, the two brightest planets from our point of view in terms of observation on Earth. Again, around 3:45 in the morning, looking east-northeast. Venus will be about magnitude minus 3.78. It's about 10 degrees above the horizon at that stage, and it's got a phase of about 79%. So that should be quite bright. And Jupiter, again, is around 10 degrees above the horizon. Its magnitude is obviously much lower, minus 1.78, but nonetheless, it should still be pretty impressive in terms of something to image if you're or indeed just something to look at. If you're up that early in August. My little written script is getting hard to read now. So moving on to the sun, obviously the one star we should be able to see lots of in the summer is the sun, but again, living in Scotland, you're never actually guaranteed that, although we've had a really remarkable spring this year, so we have actually seen a lot of the sun. This wonderful image was taken, it's up on our Flickr page by Robert Parsons. It was taken on the 20th of May this year, and it's actually inverted hydrogen alpha, so that's quite an interesting thing to see. Here's the ephemera, the sunrise times over the summer period. As you can see, this week, the week of the 1st of June, the sun is rising about 4:32 a.m. BST and setting at about 9:46 p.m. BST. That obviously gets later as we go through the summer period, but right now, as I said, we're stuck in the twilight zone. Earth is reaching, it'll reach aphelion on the 3rd of July. That's the point at which we are furthest from the sun in our orbit. We're about 152.1 million kilometres. That's the Earth's average orbit is about 149.6 million. It varies around 3% as it travels through the year, through its slightly oval. Obviously, this diagram is neither to scale nor that's not a proper representation of the Earth's orbit. So yeah, at the moment we're about 5 million kilometres further away from the sun than we are in early January. That maybe explains one of the reasons why summers in the southern hemisphere tend to be slightly warmer than summers in the northern hemisphere, considering this, we're just that small bit closer. And as we were told earlier by Dr. Vasil, as you don't need to have me repeat now, we're currently in the period of solar maximums. And I won't attempt to read out the next bit of my script because it'll just be embarrassing compared to what you've just heard about 15 minutes ago. But this is actually a good time to image the sun. However, as I think we're at length to repeat, if you are planning to image the sun, please do so safely. If you don't know how, don't look at it. Don't look at it with your naked eye. Don't look at it through an optic. Don't. We're happy to ask any member of the ASE, who we have a lot of members now who are very skilled in astrophotography, and they're also very skilled at sharing their knowledge. So please feel free to ask anyone in the society or get in contact with the president or the secretary or anyone on email, and they'll put you in touch with someone who can help you develop your skills. Speaking of skills, here are some images from our Flickr page taken by some of our members. This is an image of a lovely collection of sunspots by another one by Robert Arnold. This one was taken by Carol Gentle. This is all the way back in 2011, and according to the information she had on the image at the time, it was the very first time she'd ever taken an image of the sun. So not bad for your first go, I would say. It's certainly way better than my ever first image of the sun. I think even Galileo's was better than my first image of the sun. And finally, our dear late friend John Watson, who's no longer with us sadly, he took this very nice image back in 2015. Again, of some sunspots. So if you have the opportunity, we have both, the Society has both solar telescopes, which we can lend to members, and of course we now have our remote observatory in Spain, which also will allow you to image the sun from the comfort of your own home. Sorry? Oh, right, okay, well, I've just been told it won't allow you to image the sun from the comfort of your own home, but you can image other suns from the comfort of your own home. But we'll see. We'll see that may change in time. You never know. I just thought I'd talk briefly about Scotland's relationship with this. I don't know if anyone ever heard of the Simmer Dim, the local name for the summer sun nighttime sky in the north of Scotland, particularly if you hail from Shetland and all points Scandinavian. Simmer being a corruption of summer, obviously. I've also seen it spelt over the years with a Z or a Z, the Zimmer Dim. Obviously, when the sun is 18 degrees below the horizon, then we have astronomical darkness in the sense that the entire column of the atmosphere is within the shadow of the Earth, so we have nighttime. When the sun is between 12 and 18 degrees below the horizon, then we have astronomical twilight, nautical twilight between 6 and 12 degrees. That's where Edinburgh is right now. We enter that phase on the 1st of June this year, and we'll be there till about the 11th of July. And then obviously, if it's less than 6 degrees, then you have civil twilight. So basically think of the nighttime sky immediately after the sun has set, for the first 30 minutes after the sun has set, and you'll get an idea of why people in Shetland spend so much money on curtains. Our nautical twilight will return on the 11th of the night of the 11th of July, and as I said, in early August we'll have some nighttime sky left to us again. The moon over the summer is obviously another interesting object you can look at. These are the phases for this month. As you can see, full moon is on the 11th of June. I'm reliably told by the internet that June is called the strawberry moon. I believe in European times it used to be called the honey moon, not related to marriage, actually related to the collection of honey from bees, believe it not. But the moon itself, obviously the lunar orbit, this is just a quick little video just showing you, sorry if it's a bit blurry, showing you the orbit of the moon over time. And like all orbital bodies, of course, that orbit isn't uniform. The moon's orbit is tilted about 5.15 degrees from the plane of the ecliptic, the Earth's path around the sun. And that leads to a situation where you have the moon will appear, has about an 18.5-year cycle at where it is either higher or lower in the sky, depending on its angle to the Earth and the Earth's angle of orbit. Right now, we're actually we're in a major lunar standstill, and this happens when the moon reaches either the extreme end, northern or southern end of its orbit. And next Wednesday, which is the 11th of June, and will be the full moon, it'll actually be the lowest full moon in the horizon for about 18 years. It'll only be 5.3 degrees above the horizon at just before 1 a.m. because of course our clocks are gone forward. So in terms of that, and fittingly, it being the strawberry moon, it'll actually be quite close to Antares. The red supergiant star that forms the heart of the constellation Scorpius. So if you do have a clear and unobstructed view of the southern sky next Wednesday, which isn't always guaranteed in Edinburgh, but if you do, look south, and if you're up late enough, near 1 a.m., you'll see the moon actually at its lowest point in the night sky, as we see it from here in Edinburgh. Moving on to July, again, the full moon is obviously moving back to the calendar, as you would expect. It's apparently the thunder moon. Full moon is on the 10th, and the new moon is on the 24th. And then finally moving into August, the sturgeon moon, apparently, and full moon that night, in that month, is on the 9th. August also has 2 first quarter moons this year, as a result of the way that the calendar works in relation to the moon's orbit. So some of the planets, what are the planets doing? Some of them anyway, so I'm not going to go through all the planets, you'll be delighted to know. But these are the visibility times for the planets around the middle of this month. As you can see, Venus and Saturn are morning objects at the moment. Jupiter is not visible. It's effectively behind the Sun at the moment. Mars is setting down in the west in the evening time, and Mercury is also lost in the evening haze. Moving into July quickly, again, you'll start to notice that Jupiter is becoming more of a morning time object, and that relates earlier to the conjunction I told you about earlier on. And then finally, looking at August, Saturn is up almost all night now, but relatively low in the sky. Jupiter and Venus are now quite prominent in the morning sky. Mercury is starting to appear again in the morning sky, having gone around the far side of the Sun. So speaking of planets, as I said, Mars is getting lower in the western sky at dusk now. It's about magnitude 1.4 this month. But on the 17th, it's going to actually have a conjunction with the star Regulus, which is the kind of front paw of the constellation of Leo, and it'll be about 15 degrees above the western horizon after dusk, after sunset. It'll be magnitude about 1.4, and its phase is around 92%. So actually, in terms of imaging, that might be something people want to watch out for. It could be an interesting object to try and capture. Jupiter, as I said, currently is missing in action, but it will begin to come out from the far side of the Sun in August. When it does so, it'll be around magnitude minus 1.79. And as I referred to earlier, we've got that conjunction on the 12th of August with Venus. Saturn at the moment is at that point in its orbit where its rings are almost edge on to us. In fact, it will be that way soon. So you'll have that unusual experience where you look at Saturn and it'll look like it has no rings at all, certainly from where you're observing on Earth. Hence, its magnitude is lower. It's about magnitude 1.1 at the moment as we see it. And it's slowly getting higher in the southeastern sky from mornings onwards. But again, as I said, it's not as bright at the moment because of its orbit. So the stars, what are the stars doing? We're always interested in the stars. Well, a shameless plug for ACERO and for all the great work that's been done by my colleagues on the ASE Council in setting up the Astronomical Society of Edinburgh Remote Observatory, in case you're wondering what that stands for. For those of you who either don't know about it or haven't checked it out, it's located in Spain. It's on a mountain. It's about 1,700 meters up. It's about 140 kilometers east of Vigo, if you fancy visiting someday, or it's just slightly north of Portugal. It's at 42.2 degrees north, so obviously it gives us a much better chance to image objects that we here in Edinburgh would find extremely difficult or, quite frankly, impossible. And even on Midsummer's Day, Treviso gets about 4 hours of darkness between about midnight 26 a.m. and 4:37 a.m. They're that far south that they'll get about 4 hours darkness even in the height of summer. So it's a really good facility to make use of. Again, if you've never used it or if you're reluctant, contact members of the council. They'll be more than happy to help you make full use of the facility. That's where it is physically. I don't know if you can see that little red triangle there. That's actually where Trevinga is. And these are some of the telescopes, not all ours, I might add, but these are some telescopes at work in Trevinga. And just to give you some idea, these are just some of the images that members of the society have taken using ACERO in the last 12 months. Sorry, these are not credited, but they're all up on, they're all ASE members and they're all on our Flickr page. You can find them there. But I think they're absolutely stunning. I mean, 15, 20 years ago, this is the kind of thing you'd only have expected NASA to be producing, you know. And we now live in a world where we can do this from the comfort of our own home in Scotland. It's really quite fantastic. So even if you just go onto Flickr and look at some of the images, you don't use ACERO, I think it's it's added so much to what we can do as a society and what we can do for members. And I think, without wandering too far off the point, we're probably coming more and more into an age where we need to make the argument for science, and we need to make the argument for the spending of money on science. We seem to be traveling into an age where people now think we can simply live a modern life without really having to keep developing our knowledge as a species, which is a worrying development. But anyway, we'll move on. So looking south, I'm just going to take the middle of each of the 3 months of the summer rather than doing a far more detailed talk like our colleague Alec Pickup would have done. But looking south on the middle of this month, I suppose the main thing to point out in the south at the moment is the constellation Hercules, which will be high up in the southern sky at night. You have the famous asterism known as the Keystone, which looks like the kind of cup, I suppose, for want of a better way of describing it. There it is up close, and there are 2 objects I'm just going to point out which have often been referenced before and imaged many times by our members. The first is the globular cluster M92, which is in the constellation Hercules. It's excellent in binoculars if you get a clear sky. This lovely image was taken by our colleague Iris Tang in October of last year. If you're looking to locate it, wouldn't advise you go there. It's rather far away. But as I said, it's good in binoculars. But if you're looking to try and find it, if you take the brightest star in the Keystone, the bottom right star Zeta Hercules, and you draw a line effectively up halfway through the top and continue on again, you'll find it quite easily in binoculars. The other object, of course, is M13, which is the globular cluster in Hercules. It's got about 300,000 to 500,000 stars in it, and we know that the brightest star is a red variable, referred to as V11. If you're looking to find M13, as you can see, again, it's about halfway along between Zeta Hercules and Eta Hercules, which are the 2 stars that form the kind of the right-hand side of the Keystone. Alternatively, for finding trouble in the night sky locating it, if you find Vega and Arcturus, 2 relatively bright stars in the northern sky, most of you will know, and you draw a line from one to the other, it pretty much goes through the constellation of Hercules, and M13 is located quite close to that. This is a lovely photograph by Mike Christie of M13, and here's another lovely one by Mark Phillips of that globular cluster. And again, you know, these are the excellent objects to image in terms of ACERO. So looking south on the 15th of July, which is about a month from now, well, I guess the other thing to point out at the moment is that there will be more or less a conjunction of the Moon and Saturn in the dawn sky. Again, it's this is you know, daylight is getting quite bright early on, so I'm not going to labour too much on what's happening in July. And then, of course, in August, we've got the Summer Triangle, which is the asterism where you join the stars of Vega, Deneb, and Altair in Lyra, Cygnus, and Aquila, the Eagle. And that's quite a good object to look at. Saturn is also becoming more prominent in the southeastern sky throughout the month of August. And another object you might like to try and find during the month of August is the globular cluster M15, which is just at the head of the horse of Pegasus. If you follow the curve coming off the great square of Pegasus, the horse is upside down as we look at it. This is its head and its body. This is a very nice image of M15 that was taken by Hugh Somerville. And looking north, briefly, of course, in August, we also have the Perseid meteor shower, which comes to its peak around the 12th of August. It starts on the 17th of July until late August, but it comes to its peak around the 12th of August. Unfortunately, this year we've got a waning gibbous moon at around 91%, so magnitude about 12.6, minus 12.6, so it could be harder to see some of the meteors this year, but nonetheless, give it a try. It's not the only meteor shower. I'm just going to mention this, that there's another second meteor shower in August in Piscis australinid, which is the southern fish. constellation, not something we see very often here at far north of Edinburgh, but it is low in the summer sky if you have a clear horizon. The radiance of meteors rather from this meteor shower is only about 4 degrees above the horizon, and again it's just before dawn. But if you look at it, basically it's 29th of July. This is Piscis australis, the southern fish, which as you can see is right down the southern sky. That's the kind of the radiant point. It's not great. It's not a great. It probably wouldn't be a very great meteor shower. It's at best it's about 5, I think, meteors an hour in perfect nighttime conditions, which we won't have here. But nonetheless, I just thought I'd point it out as the Perseids aren't the only show in town when it comes to meteor showers during the summer. And finally, as we always finish up, I think we do, with noctilucent clouds. This is a lovely image by Ramsay MacIver of noctilucent clouds here in Edinburgh. Of course, mid-May and mid-August, or rather mid-May or mid-August, I should say, are the best time to see them. They're blue and silverish in appearance. They appear when the sun is roughly between 4 and 16 degrees below the horizon, so obviously summertime in Edinburgh is ideal for that. As we know before, and has been said in many presentations before, the literal translation means night shining cloud. They're formed by ice crystals. You need thin air and thinner water vapor and a dollop of dust and lots of nice cold temperatures in the upper levels of the atmosphere for these clouds to form. Here's another very nice image taken here from Edinburgh by John Briggs. They form at a height of about 80 kilometres, so they're still visible about an hour after sunset because that part of the atmosphere is still illuminated by the sun. As I heard another member mention a while back, and I hadn't realised this, but apparently there's at least no written record of noctilucent clouds having been recorded pre the Industrial Revolution. So there's some debate as to whether pollution in Earth's atmosphere may play a role in either the development of these clouds or in us being able to see them from the surface. But finally, Earth, of course, isn't the only show around when it comes to noctilucent clouds. This lovely image was taken by the Curiosity rover on Mars in February of this year of the Martian version of noctilucent clouds. So even in an atmosphere as thin as Mars, there's hope for noctilucent clouds yet. So have a very happy summer. I hope it's as warm and pleasant as it's been in the spring. Hopefully you will have less fire, more water, and as much air conditioning as you need. Thanks very much.
Thank you, Sean. That's it for our YouTube viewers now, so we're going to turn that off. So thank you for joining us, and hopefully we'll see you at the next